Recording. Okay, so it's nice to present Emiliano Acri from Universidad de Buenos Aires. He will talk about multipermutation solution to the Yang-Baxter equation. Thank you, Emiliano.
Thanks, Monique, for the introduction, and hi, everybody. Thanks for being in this talk. And thanks to all the organization for inviting me. Well, as part of my PhD, I will present this joint work with Leandro and Rafael related to multipermutation solutions to the Yang-Baxter equation, and we'll see the meaning of this in just a few moments. First, let me introduce the theoretic Yang-Baxter equation for a given set X and a map from X times X to X times X. We say that the pair XR is a solution to the theoretical Yang-Baxter equation if this equality holds. That's the Braille equation. So this notation is quite usual. We will particularly interested in solutions where the coordinates are a permutation of X and Y, and in the first coordinate for any fixed X, we want a permutation of Y, and the other way in the second coordinate. So we'll say that the solution is finite if the set X is finite, and is non-degenerate if both the sigma X and tau X are permutations for every X. And we'll say that the solution is involutive if the square of the map is the identity of X times X. So in what follows, whenever I say a solution, I mean a finite non-degenerate solution, and an involutive solution will be a solution involutive. Okay, so an easy example of a solution is this map where sigma and tau are fixed permutations that commute, and this solution will be involutive if and only if the tau is the inverse of the sigma map. So Ettinghoff, Schedler, and Soloviev, they define some algebraic structures related to the solution, and one is the structure group of a solution, which is presented like this, where the operation is given by the circle. And this group admits a finite quotient, which is quite useful from a combinatorial viewpoint. And for the special case of the involutive solutions, this quotient is known as the permutation group of the solutions, and it's the group generated by the sigmas, sigma X. You can also take the taus. The solution being involutive implies that the group generated by the sigmas or the taus is just the same. So we'll define a class of the so-called multipermutation solutions for the involutive case first. We can define this equivalence relation. Two elements are related if and only if they induce the same permutation, sigma. So we have an induced solution on the quotient of X by this relation, which is the retraction of the solution. So we can define recursively the nth retraction of a solution by taking the retraction of the retraction. So we will say that the solution is irretractable if the retraction is just the same. So all sigmas are different. And if there exists an n such that the nth retraction is the singleton, we refer to this solution as a multipermutation of level n, where n is the minimal positive integer. So Ettinghoff, Scheller, and Soloviev noted that almost all small examples of solutions are multipermutations. So this is a class of great interest to study. We have a characterization of the multipermutation solutions in terms of the structure group. First, recall that the group is said to be left orderable if there exists a relation of order, a total order, on G preserved by left multiplication. So we have this theorem for involutive solutions. Solution is a multipermutation solution if and only if the structure group of the solution is left orderable. And this first implication was known from independent results of Jespers and Ogninsky and Shuraki. And a more difficult study was needed to prove the equivalence. The work of Bachicher, Sedot, and Bendramin proved the other implication using a more geometric approach. And we'll need this theorem in just a moment. Before that, we have a geometric characterization of the structure group of an involutive solution. And due to a theorem of Gateva, Ivanova, and Vandenberg, we know that the structure group of an involutive solution is a torsion-free Bieberbach group of dimension equal to the size of the set X. And in our work, we have an explicit description, which is called the translation group and the holonomy group of a Bieberbach group. And the more important is the holonomy group, which is the permutation group of the solution generated by the sigmas. And we use this characterization to prove this theorem. If all the Sylow subgroups of the permutation group are cyclic, then the solution is a multipermutation solution. And to prove this, we made use of several results of Kionke and Rimbaud on Bieberbach groups, and the work of Lebed and Bendramin on structure groups of involutive solutions. We can see that the hypothesis of on the Sylow subgroups implies the left orderability of the structure group, and this is equivalent to X being a multipermutation, as we have seen. Well, when the permutation group is cyclic, this result was known by from the work of Ettinghoff, Scheller, and Soloviev again, but the proof is by induction, and our proof needed the geometric approach. So an interesting question is whether or not the converse for this theorem holds, and the answer is easy. We have this toy example, which is a multipermutation solution that is involutive, but the permutation group is the Klein 4 group, so the unique Sylow subgroup is not cyclic. So another interesting question is if we can extend this theorem to the non-involutive solutions. But for non-involutive solutions, we no longer have Bieberbach groups, and we did not define the permutation group for this case. But we will achieve a similar result by a quite different approach. First, let me introduce this algebraic structure called skew brace. Left skew brace, we have the right version. A triple A plus circle is said to be a left skew brace if the set A with both operations is a group, not necessarily abelian. This is just for historical reasons. and such that this compatibility condition holds, similar to a distributive property. Well, a similar structure was defined by Rump to study involutive solutions, and equivalent notions appear in the works of Tingoff, Schedler, and Soloviev, Lu, Yang, Su, and Soloviev. This structure is quite similar to a ring, so we can use group theory to study solutions, as we were doing so far, and with this new structure, we can also use tools from non-commutative ring theory. So we say that skew brace is of nilpotent type if the additive structure is a nilpotent group. And this is important because we want to imitate non-commutative ring theoretic properties. And also from the work of Tingoff, Schedler, and Soloviev, we know that finite skew braces of nilpotent type have a solvable multiplicative group, and this is quite important. So this first example, the trivial skew brace, is the one with where both operations coincide, and a lot of samples, more interesting samples are coming from radical rings. Recall that the radical rings, in the sense of Jacobson, is a ring such that this operation, this circle operation, plus and star are the operations for the ring, and this circle operation turns the underlying set R into a group. So this set R with the addition of the ring and this circle operation is a skew brace. Well, for any given skew brace, we have this lambda map that defines an action of the multiplicative structure over the additive group, and it's given by this formula here. An important theorem that relates skew braces to the Yang-Baxter equations is this one. For any skew brace, this map here is a solution to the Yang-Baxter equation, where this prime stands for the inverse under the circle operation. And we have that the solution is involutive if and only if the additive structure is abelian. And under this assumption, if the additive group is abelian, the permutation group of the solution is just the image of the lambda map. Well, similar results were known, again, by Rump, Tingoff, Schedler, Soloviev, Lu, Yang, Su, and Soloviev. We have a sort of converse to this theorem. I mean, for a given solution, we can define a unique structure of a skew brace over the structure group of the solution, such that the induced solution is an extension of the original solutions. And the quotes are because the canonical map, this one, that identify the elements of X with the generators of the structure group, is not necessarily an injection, but we have this equality of maps, and if the solution is involutive, then this is indeed an injection, and so the R sub G extends the R map. So this result arises in the work of Tingoff, Schedler, and Soloviev, again for the involutive case, and in the work of Lu, Yang, Su, and Soloviev for the non-involutive case. So what's the conclusion? All solutions can be studied through skew braces, and the involutive solutions are related to skew braces of abelian type. So let's recall some structures related to skew braces. So for any skew brace, we have this star operation defined as A star B equals lambda sub A of B minus B, or this equivalent. This is the definition of the lambda map. And remember that this is the product operation for the case of radical rings, the way we define the circle operation. So this is the corresponding star operator. So with this operation, it's easy to define the notion of an ideal. It's a subset of A, which is a normal subgroup of the additive structure. And it is stable with left and right multiplication using the star operation. So the trivial skew brace, which is the one where both operations coincide, is equivalent to have a zero star operation. So a natural generalization of these trivial skew braces, we can think nilpotent skew braces, requiring that the star operation of n arbitrary elements vanishes. But the problem with this definition is that the star operation is not associative. So we have two notions, a notion of left nilpotency and a notion of right nilpotency. So I'll discuss briefly each notion. Well, our goal was to study non-involutive multipermutation solutions. And since we have this structure of skew brace, we will translate the problem to this language. And we have this sort of ascending central series. We start at 0, and the next ideal is the intersection between the kernel of the lambda map and the center of the additive group. This is the so-called socle of the skew brace. And for the next ideals, well, since the soc n-1 is an ideal of A, the quotient, this quotient is defined. So we can take the socle of this skew brace and identify this socle with an ideal of A that contains the soc n-1, as it's usual in ring theory, same. And we say that the skew brace is a multipermutation if there exists an n such that A equals the soc sub n of A. And by a theorem proved by Sedos, Moktunowicz, and Vendramin, we know that multipermutation skew braces of nilpotent type, important, are exactly the right nilpotent ones. So we characterize multipermutation skew braces using this nilpotency notion, the right nilpotency notion. In our work, we defined the notion of right p nilpotency for every prime p for skew braces of nilpotent type. So we can prove this, that skew brace is right nilpotent if and only if is right p nilpotent for every prime p. And the next step is to have some criteria that ensures the right p nilpotency. So we have this theorem. If the multiplicative structure of the skew brace has an abelian normal p-zero subgroup for a prime p, then the skew brace is right p nilpotent. And some particular cases of these results were proved by Ballester Bolinches, Esteban Romero, and Meng. We have this generalization. So finally, we get the analog result we were looking for in terms of skew braces. if every zero subgroup of the skew race of the multiplicative structure of the skew race is cyclic, then the skew race is right nilpotent. Yeah. Okay, so now we will briefly discuss the left nilpotency. We have this theorem of Smoke-Novix. Says that if A is a radical ring, the left nilpotency of A ring is equivalent to the nilpotency of the circle group of this ring. Since she used techniques related to skew races, so in a joint work with Edo and Bendramin, they extended the result to skew races of nilpotent type. And this is the most general case, since removing the nilpotency hypothesis on the additive structure fails. The trivial skew race, for instance, so any non-nilpotent group is a counterexample because the star operation vanishes because it's a trivial skew race, so the star operation is 0 for every pair of elements, but none of the groups are nilpotent. Well, we pick a non-nilpotent group as additive and this result from a different viewpoint, which is more conceptual. And we made use of these two results. First, the left nilpotency of the skew race is equivalent to a notion of left p nilpotency for every prime p, as we did for the right nilpotency case. And then this left p nilpotency is equivalent to the multiplicative group being p nilpotent. This means that there exists a normal whole p prime subgroup that's a maximal normal subgroup whose order is coprime to p. And that's all. Thank you all.